Hi everyone, welcome to Honors Chemistry. I'm your teacher, Ms. Belinsky. This will be the first of the voice lectures that I will provide in case you missed a lecture or want to just review what I taught you in class. So these will be posted in open class for your reference. Alright, so we do start the year with just an introduction to what chemistry actually is. This year we're dealing with materials and how to change those materials. So biology was more life science, you dealt with processes in the human body, how animals interact. In this course we look at what I call just stuff that's on the planet, in the universe, in the world around us, and then we attempt to change it and figure out why those changes occurred. And that's why I included this statement. Chemistry does involve a lot of problem-solving techniques. And actually what I hope you achieve in this class is a way to think differently, how to think about problems and attempt to solve them. So you may not be interested in chemistry for your future, but you are taking this course to push yourself. So one of the ways you can do that is to train yourself to think better. Alright, so we do start with the same type of problem-solving technique that you should have learned in biology, physical science, and you'll continue to use this in physics, anatomy, or whatever other course you take. It is the scientific method. It is the best way to solve problems in not just chemistry, but in any science. So what you do is make observations. This is where the information becomes known to you. You make a hypothesis, which means you suggest a possible explanation for some situation. When you experiment, you perform the steps to search for new information, and it's the best part of any science class, in my opinion. Now, when you take data, your data this year will be much more specific than in biology. You will be recording your measurements from your experiments, both qualitative and quantitative. Qualitative is like a description, like color, does it smell? Quantitative will have something to do with a number. So maybe you'll take the temperature in degrees Celsius, find a mass in grams, something of that nature. The analysis will be one of the most difficult parts of your experiments this year because you have to try to understand why things happened. Now in our class, we are supposed to know why things are happening because you have a set experiment or a set of procedures that you're supposed to be doing. If you were to do this beyond high school, beyond college, people that are working for their PhDs, they're attempting to find things that aren't necessarily known. So that's even harder than what you'll be dealing with. And that's what leads to the conclusion. You will not get a chance to repeat your experiments just for the sake of time. When you get to college, you will be able to repeat them a couple of times to try and get the right answer. But if you're doing this on a larger scale, like figuring out if a medicine's going to work or if a food product is healthy, you have to keep testing it. A lot of people have to agree with what you're doing, and then a conclusion can be made. And if it is agreed upon over a long period of time, it can become a model or a theory. So what is the difference? A theory is attempting to explain what you're observing, but it's not quite 100% true. In biology class, you learned about evolution, which is that things have changed over time. We have a lot of evidence for this, and we keep finding evidence, but it's still not 100% proven. I mean, we know this to be true based on what's happening now, but still, we can't go back in time and be there. All we can do is look for the evidence to help prove it. But a law, though, is something that is observed, and 100% everybody agrees about it. It cannot be changed, and the best example is gravity. So if you throw something up, it is going to come down. Alright, and just one more time, I want to emphasize that you will be trying to solve problems in this class, and hopefully use some really good critical thinking skills. And that's why I included my little picture down here. To really be intelligent, you have to continue to question things. Question yourself, question me, question what you're looking at, because it will expand your mind, okay? So you should question even the things you think that you know, because you might find something that you didn't. Alright, and we do roll right into chapter 2, which are the measurements and calculations, and you need to know this up front because you will be doing a lot of lab techniques in this class, and you have to know how to take your measurements. Alright, so a measurement really is a qualitative observation, and you have to give them some meaning, and the meaning is the unit. So you'll always find some number that you're measuring, but I need to know what that number means, and so do you. So a good example is your paycheck. If you get a paycheck that just reads 5, is that 5 cents, $5, 5 hours? What is it that that 5 means? And that's exactly what I want you to do in the chemistry class. Alright, so how to write your measurements. The first thing we need to do is figure out how to write them concisely. So there are really, really big numbers and really, really small numbers that we don't want to write all those digits out for. So there is a concise way of doing this. It's called the scientific notation. So you have your 2 rules here that I'm not going to explain. I just hope that you understand how to use them as we go through our examples. So you'll never have to write these down, but you have to understand them. Alright, so in this first one right here, this distance from the Earth to the Sun, so you see 93 with a lot of zeros. So instead of writing all that, if you had that value, there's a better way to put it. And the first thing you want to do is find a number between 1 and about 9.9. So it can't be 0, can't be a decimal, and it can't be over 9.9. So the best number is right here to your first one. It's 9, and you will put 0.3. So you're going to put a decimal right in here. And scientific notation is based on the power of 10. So then you write times 10, and then what you do is count how many places till you reach that 9.3. So you start at the end here, and you move it. So 1, 2, 3, 4, 5, 6, 7. So that becomes 9.3 times 10 to the 7th. And that 7 is positive because you are dealing with a large number. Alright, next, the 125, and I hope you're practicing these as you have your notes in front of you. The first rule, you would pick the number, it's going to be 1, and then you'll put your decimal, and if it's not a 0, you do need to write that number. So this becomes 1.25, and it's times 10, and what is your exponent? You start at the end of the number and work your way back, 1, 2. So 1.25 times 10 to the second. Alright, and in letter C, you have 1700. So the first rule, you're going to put your decimal here. It'll become 1.7, and you don't need to write the zeros. They'll become the exponent. So you write times 10, and you start at the end, 1, 2, 3, 3 decimal places. So 1.7 times 10 to the third. If you did actually write 1.700, you're not wrong. You just gave yourself more work, so it's not as concise. Alright, now what about the opposite direction? You can see these are decimals, and some are pretty large decimals here, so let's try this one. The first rule still applies. You'll put a decimal after 1, so it becomes 1. And you can either just leave it 1 point, or you can put the 1.0 if you want to, but you don't have to. And it's still times 10. Now, when it was a larger number, we started to the right and worked our way to the left. Now you're going to start at that decimal point and work your way to the right, where you placed it for making scientific notation. So what I mean is you start here, right? And you're going to move it 1, 2, because that's where I put the decimal place. So this becomes 1 point times 10 to the negative 2, because we're dealing with decimals. Here, this will become 1.67, and then you start at that decimal point and work your way back. 1, 2, 3, 4. So 1.67 times 10 to the negative 4th. And then here you have 8.9, and your decimal place moves 1, 2, 2 places. So 8.9 times 10 to the negative 2nd. Alright, so just a general rule, if your power of 10 is positive or your exponent is positive, you move the decimal to the left. If your exponent is negative, you'll move the decimal to the right. So if you missed class, then I hope you try these by yourself. So kind of pause my lecture because I'm going to give the answers right away. So go ahead and try these 3 and see if you get the right answer. This is now actually taking the number out of scientific notation. Alright, so if you were in class, then you saw this becomes, you start at the decimal, this is a positive 5, so you move that decimal 5 places to the right, so 1, 2, 3, 4, 5, and the number reads 280, 000, 280,000. This one, 1.5, so you start that decimal, and you move it 6 places to the right, so it becomes 1,500,000, or 1,500,000. And then our last one, you see you have a negative number, so you will now move it to the left to take it out of scientific notation. So that's 1, 2, 3, 4, and your number is 0.00043.